So continuing with last lecture, we are going to talk about distributed training, right? So we are going to talk about gradient compression to tolerate the bandwidth limitation, right? In the last lecture, we talked about we need a huge amount of communication bandwidth when we have increasing number of nodes, right? So for example, in our lab, we have tons of GPUs, and how do you scale your training to many GPUs? So we want to talk about a gradient compression technique to reduce the bandwidth requirement. And the other challenging part is the latency requirement. So we are going to talk about delayed gradient averaging, right? Just like you want to, sometimes you want to have some late days for your homework. This is exactly the late days for distributed training. So here is our agenda. First, understand two concepts. One is bandwidth, the other is latency in distributed training. Okay? And overcome the bandwidth bottleneck by gradient compression, and then overcome the latency bottleneck by delayed gradient updates. Okay. So let's start with the first section. Understand the bottlenecks in distributed training and what makes it difficult to scale up the number of nodes. Okay. So we talk about distributed training motivated by we are having increasingly larger amount of training data sets, right? A lot of text to train with GPT models, for example. So this requires a lot more computation, and also large models require more memory to fit the model, and also user privacy. Sometimes we cannot even transmit data to the cloud. Distributed training make it possible to parallelize across different GPUs and different nodes. Okay? But communication soon becomes a bottleneck as you scale up the training to a lot of nodes. So remember, we talked about this parameter server centralized training scheme where we have a centralized parameter server that coordinates across different workers to be each worker. We are using the data parallelism. Each worker has its own copy of the training data. Okay, so each worker is going to calculate the local gradients. Okay, and it's going to send the local gradients to the parameter server. So the parameter server is going to accumulate an average of gradients and update this neural network model. Okay, so this push and sum also requires synchronization across different training workers, right? So that becomes the bottleneck for the whole system. For example, here are here is the bandwidth requirement for different benchmarks during training. Okay, so this is assuming using NVIDIA 2080 Ti GPU, batch size of 32, unit is millisecond. So from Resnet 50. Each iteration time is about 330 milliseconds. So considering we have to transmit about 25 million parameters. Okay, so this is the size of the weight, which is equal to the size of the gradient. Right? So this is the amount of data we have to transmit within this amount of time. Right? So every second we have to transmit 2.3 gigabits per second. Similarly, for like swim transformer for tiny and large, we need to transmit about between 1 to 3 gigabits per second. So the conventional normal Ethernet bandwidth, if you don't have HPC configuration, is just 1 gigabit per second. Like we have like 25 gig per second high-speed networking, but that becomes pretty expensive, right? So how do you train and scale the model without relying on those high-end networking, right? So that's the motivation of this lecture. Okay, so as we scale up the number of training nodes, if you have more communication steps, longer latency, soon this part becomes the bottleneck, right? So this is the ideal scale up. Ideal speed up as you have more number of GPUs. Most of the models is not ideal, especially those big models. So this is comparing AlexNet, Inception V3, and ResNet 152. And you can guess why AlexNet has the worst scalability. when you have 250 nodes, the theoretical speed up should be 250. But why LXNet is the worst? Only 150x speed up compared with using just one single GPU. Consider the time required by computation versus communication. Right, exactly. So LXNet has a huge amount of parameters, okay, 60 million parameters. And also the computation is low, only about 1.5 around that giga operations. So therefore, the ratio between communication versus computation is really high. Right? We do a lot of communication, but just a little bit of computation. Therefore, the scalability will be bottlenecked when you have a large number of nodes. All the time is spent on communication across 250 GPUs. Right? So when we are designing the model, we should try to design the model which has smaller model size, right? So that we have smaller gradient. So that will reduce the amount of communication bandwidth requirements. So actually, computation is cheap. It's very easy to increase the amount of flops, the multipliers, the adders. But memory bandwidth and networking bandwidth is really the lower bar in the bucket, right? So the lowest bar determines how much water you can hold in the bucket, right? So here, data movement, which is consisting of two parts: memory, moving the data in the memory, and also across the networking. Okay, so the poor networking bandwidth and intermediate connection for these cellular networks makes it quite difficult to do such distributed training over poor networking condition. For example, across different edge devices. Okay, so given that kind of motivation, let's start to talk about gradient compression techniques to reduce the communication bandwidth in distributed training. So we recall this workflow for this parameter server-based distributed training, where we have a parameter server, and then different workers pool the parameters, do the local calculation about the local gradient, and then push the gradients to the parameter server. Okay. And when we are pushing the gradient, rather than pushing the entire gradient tensor, right, can we selectively push only a couple of a subset of the gradients? And remember, during inference, we talked about pruning, right? At that time, we were pruning the weight, right? Now we are trying to prune the gradient. Okay? So we can actually drastically sparsify the gradient tensor up to 99.9% of the parameters, the gradients, can actually get pruned to be zero, right? So we only need to send those non-zero parameters during non-zero gradients, okay, during the communication, which can drastically reduce the communication bandwidth requirement. Okay? And remember, during pruning, weight pruning, how much parameter can we prune? In your labs, 10%, right? 30%, 10% density, right? So you can prune away around 70% to 90%. That's it. If you remember, we did the experiment when we are pruning 99% of the parameters, the neural network has almost zero accuracy, right? But actually, the gradient pruning is not like that. It's more robust pruning. We're going to show our experiments that actually we can prune away 99.9% of the gradients without losing any accuracy, which is pretty exciting.
So training can take longer to do
no, it doesn't. Actually, using the same amount of iterations, still converges well. So we're soon going to introduce that technique. And then another technique, remember we talk about quantization for efficient inference. Now we try to see whether we can quantize those gradients. Right? If we can quantize everything to 8 bit, then we need only 1/4 of the communication bandwidth compared with if we have to send everything in FP32. Right? So those are the two techniques we are going to cover to reduce the communication bandwidth. Okay, so here's the agenda when we are talking about gradient compression. Okay, so the goal is to reduce the size of the gradient from two perspectives. Okay, one is gradient pruning to reduce the number of gradients. Second one is gradient quantization to reduce the bit width per gradient. Okay, so we are going to introduce several techniques for both directions. So let's start with gradient pruning to reduce the number of gradients to be exchanged. Okay, so let's start with the baseline method. Okay, with local gradient accumulation. So this is original tensor gradient tensor, okay, a 4x4 tensor. Similar to weight pruning, we can sort them and only keep the largest, the top k entries. Okay. For the remaining gradients, we can zero them out. Just completely don't need to send them to the parameter server or to its neighbors. Okay. So how do we deal with those zeros? Imagine this is a full tensor. We have 16 gradients, okay? But we are going to send out only 4 gradients, either to the parameter server or to the neighbor. So what shall we do for the remaining 12 gradients? Do we throw them away, or is there any more clever way to deal with it? Right, you can accumulate that locally, right? You don't need to send them out, right, to save the communication bandwidth. But locally, you can accumulate those weights in the next iteration, right? You can still apply these gradients which didn't get sent out, but you accumulate those gradients locally on your own model. The parameter server didn't see that, your neighbor didn't see that, but yourself, this worker can get this update, right? So we can pass this residue to the worker itself to update its local copy of the weight, right? So assuming after a couple of iterations, say this is 0 gradient, okay? Say this is like a super small gradient, like 0.01, just give an example. 0.01, that's applied to the weight, okay? And maybe next, in a couple of iterations, it will be above a certain threshold, then it will be sent out. Okay, so this accumulation is very important. Yeah.
So did the residual of the accumulation that we accumulated to the gradients, the local gradients, or we also I'm confused. So we accumulate the gradients, but we obviously also update the parameters, right? By using locally, by using for.
So for this gradient, what is the question?
So this is just gradients. What do we do for the weights? We update them normally.
So we accumulate the residual in local gradients, but we didn't apply these gradients to the local weights. Local weights will be updated using the specified gradients.
Oh, okay. Yeah. Okay. Okay. I see.
Yeah. So you have a buffer to save these accumulated gradients, but didn't apply that until it reaches a certain threshold, then we'll send it out. So this is the training speed, right? So we can drop 0%, then we can process like 13,000 words per second. But if we can drastically reduce the number of gradients to be communicated, actually there is noticeable improvement about the word per second, so images per second during training. Okay? However, this method alone fail on modern models, like big models like REST. Right? So for example, this method have 93.75% of accuracy, but with such sparse communication, there's about 1% degradation of training accuracy. Okay? Using REST even on Scipher. Since such sparse communication itself is not enough, so let's think about what leads to the poor accuracy, okay? By using this naive gradient dropping. What could be other factors that we ignored?
Could we just always be sending the same parts of the gradient and they just dominate and the other ones never really return to, like, even if it's a really small accumulates, there still might be something bigger that's
important, but never sent out.
yeah, like can we tell it like, hey, use position this like 5 times in a row, like take turns basically.
Right. Some gradients might never get this opportunity to get sent out. Right? So, so actually, that's momentum that is leading to this kind of incorrect gradient sent out. That's a different thing, but what you mentioned definitely makes sense. But here we want to mention is another factor that lead to the poor performance in gradient dropping. Okay? So previously we were assuming just doing standard gradient descent. Okay? So which is the new W is equal to the previous W minus the learning rate times the gradient. But actually, momentum is widely used during training, and the previous method didn't consider the momentum. Right? So momentum is actually an extension to the gradient descent, where we have to which can overcome this local minimum oscillation of the super noisy gradients. Right? So let's see what is momentum. Say this is the gradient, okay, and this is the previous update. Okay, so t minus 1 the update, the weight gets updated in this direction. Okay, and we multiply that with a momentum m on top of this original gradient. Right? So rather than directly following the direction of gt, we are adding gt with the momentum times the previous update. So this is actually denoising, kind of smoothing across the previous weight update versus the new weight update. Okay? Without such momentum, if we get a direction in this way, we will directly update the weight in this direction. However, with momentum, we're going to have a weighted sum of the previous direction versus the current direction. In case the current weight is the current gradient is super noisy, or it might be even a wrong gradient. Right? So this method, it acts as a smoothing method for the previous update versus the current update. The sum will be the current direction of update. Right? So mathematically, this is the direction of the previous update. U, okay, we call it velocity. Velocity is the vector that actually is updating the weight. Right? So weight is equal to the previous weight minus the learning rate times the velocity. Okay? And velocity equal to the previous velocity discounted by a factor of momentum, okay? Something smaller than 1, plus the current gradient. Okay? So using this smoothing method, we can actually do the update in this way, okay? Rather than using GP. So for the next timestamp, we are going to repeat this process where this is the actual gradient, and this is the previous update times the momentum. Okay? Even following the same direction as the previous update. Say the new gradient is pointing to this direction, the sum of the momentum and the gradient will point to this direction. Okay? So this is widely used in both vision and NLP tasks. Okay? So we are going to repeat this process to do the update in this way. Okay? So we are actually updating using the velocity. rather than using the gradient. Okay, so blue part is the gradient, and the green part is the velocity. So what happens if we directly accumulate the gradient, but we are actually using the velocity to update the weight? So first of all, is everyone clear what's the difference between the gradient versus velocity? This is gradient, and this is velocity. Feel free to raise your hand, and I'm happy to clarify that again. So we are just using, if we use conventional approach without momentum, we are doing update using weight equal to previous weight minus the learning rate times the gradient. But actually here we are actually smoothing that by introducing momentum. So this is a new gradient, and this is old velocity. This is a new velocity. Okay, new velocity equal to like something smaller than 1 times the old velocity plus the new gradient. Okay? So what if we just directly accumulate the gradient without considering the momentum? So this is vanilla SGD. This is with gradient accumulation, right? So the old gradient, this is the new gradient, and this is accumulated version. So if we consider this is momentum during the update, actually we are going to update in this direction, which is quite different from the original update vector. Right? So this is obviously not correct. So this is showing that just accumulating those gradients that is super small, they are unlucky, they didn't get sent out because their magnitude is so small that they got pruned during this gradient pruning process. So we are going to accumulate them locally, right? So this is the accumulated result. Okay? Say at a certain point, it is getting pretty lucky, it becomes a bigger one and gets sent out. It didn't get pruned, so it will be added with the momentum, and this is the final result, which is different from if it didn't get pruned but updated twice. Right? So the optimization status will shift. They no longer match. So we don't want that situation to happen. Right? So instead, how do we solve this problem? What should we accumulate? So we should actually accumulate the velocity, okay? The green vector, rather than the gradient. We shouldn't accumulate the gradient, but we should accumulate the velocity. So if we accumulate the velocity, the final result is actually the same. So this is comparison between vanilla momentum SGD versus if we do gradient pruning without momentum correction, which is going to get a wrong direction, versus if we add this momentum correction. So the direction will be the same as before. Okay, so the third technique for gradient function.
You get a velocity after all the gradients are averaged from the center node. So you have to on the node level, you have to get back the velocity back and so because the velocity is calculated by averaging all the gradients.
Velocity is calculated by averaging all the gradients.
And
yeah, this is the local version of that without considering. So what is exactly the question? So
yes, so the local nodes have to get the velocity back from the single node.
other nodes.
Or is it just but this is a velocity
you actually compensate the linear from personal application, basically it should be sigma the velocity plus sigma the gradient. And you actually on different ways, you put in the whole version of the gradients. And from the server side, you actually continue
Okay. Okay, so the next method is actually the warm-up training, right? So in the early stage, we find there's very drastic change of the weight. The gradient magnitude could vary a lot from gradient to gradient, right? So the local gradient accumulation and will lead to this thing called a staleness, right? So you're going to have a stale gradient, which has been accumulated from actually a couple of iterations ago. It's not new gradient, right? So it will make the problem worse since the training changes so rapidly. The stale gradient will hurt this training dynamics. So we want to avoid it by using this warm-up learning rate warm-up, right? So we want to start with a smaller learning rate to linearly scale the learning rate, so that in the beginning we want to have don't want to have the gradient to change so drastically. Okay, and also we want to warm up the sparse, okay? Rather than directly make it very super sparse. We want to gradually make the gradient to be sparse, okay, to avoid this sudden change in the sparsity, but we gradually make the increase the sparsity, okay. And also here we empirically chose to exponentially increase the sparsity in the first couple of epochs, okay, to make the optimizer adapt to larger sparsity. Okay, so let's see how does it work when we have 99.9% sparsity, meaning that only 1 in 1,000 gradient is actually gets communicated. Assuming 8 GPUs, okay, so naive gradient pruning actually didn't converge with resin 110 on the SciFi 10 data set. So what if we add this local gradient accumulation? Okay, so some degradation of accuracy at 1.5%. What if we add this momentum correction? It's getting better. Only 0.36% loss of accuracy. Or we can add this warm-up training, maybe 1% loss of accuracy. But actually, we can combine all the techniques, including local gradient accumulation, momentum correction, and also the warm-up training. Okay, so we can finally recover the accuracy a little better, maybe due to noise. Right? So on the right-hand side, it's showing the word error rate for a speech recognition task. It's similar findings. So the lower the better for the word error rate. By combining all these techniques, including local gradient accumulation, momentum correction, and also the local gradient clipping, since in LSTM and RNNs can suffer from this gradient explosion effect. So we have to clip the gradient if it is above a threshold. And so by combining all these methods, deep gradient compression, DGC, can actually fully recover the error rate. So this is the learning curve for resin 11 on SciFi 10 versus resin. So this is actually the accuracy versus the loss. Okay, so this is a comparison of different methods. So the blue one is the baseline, actually the purple one is the deep gradient compression. Okay, so they can actually match super well. Here. So not only on SciFi 10 dataset, what about we use large scale dataset on ImageNet? So this is comparing the accuracy of the baseline, the dense gradient exchange versus the sparse version, the TGC version. So this is again 99.9% sparsity, only 1 in 1,000 gradient gets communicated. So we can fully match the top 5 accuracy and save the communication requirement from 232 megabytes to only less than half a megabyte. right? So this is almost 600 times reduction in the communication bandwidth. And why we didn't save 100 or 1,000 times if the percentage of sparsity is 99.9%? Actually, we have to communicate the index to represent the sparse matrix. Right? We have to store either in COO format or CSR format or CSC format index format. Secondly, the biases, the gradient of the bias, since it's one-dimensional, we didn't prune the bias. So for those two factors, actually we didn't get a theoretical saving of 1,000 times, but the measured saving is actually 597 times. On the bottom is showing UGG image. So accuracy, again, well maintained. The compression ratio is about 277 times. So apart from image classification, this is language modeling. Again, with only 1 in 1,000 gradient is maintained. So here we can have about 462 times reduction of the communication bandwidth, fully matching the accuracy and also the loss during the learning curve. Okay. So this is another model showing the speech recognition, right? So showing the word error rate is well maintained, and the learning curve is the same. So any problem here? So far we talked about the gradient saving among a single node, right? What happens if we do this all reduce operation, right? If you just send your data to the parameter server, just only once, one-to-one communication, that's probably okay. But if you have this all reduce without this centralized parameter server, but you want to do distributed training in a decentralized manner, problems occurs. Say these are the gradients of node 0, node 1, 2, and 3. Right? So now node 3 send its gradient to node 1. Okay? So the sparsity pattern is different. So after that, node 0 becomes a lot more denser than node 1, than node 0 initially. Right? And node 0 is going to send this vector to node 1. Okay? So they also have different sparsity patterns. So as a result, node 1 becomes denser. So the more you send, the denser you get. Right? So after a couple of iterations, for example, after the second iteration, these two numbers will become non-zero again. Right? So it will get denser and denser as you have more iterations of this reduce operation. Okay. So let's see, how do we solve that problem? People propose this power SGD, okay, which is using another method to reduce, to prune this gradient, actually using low rank approximation. Right? So rather than pruning those smaller gradients, power SGD want to use this low rank representation. That we have learned a matrix can be represented or approximated by a low rank approximation. Right? So this smaller dimension that we are keeping only one rank of 1 in this scenario, right? So that we need to send only 8 gradients rather than 16 gradients in this example. Right? And people find actually if you keep a rank of 2, that is good enough, right? So this is the number of workers versus the speed up. So rank 2 can maintain a pretty good speed up compared with other methods using different backends like NCCL, etc. Okay. And also the accuracy is also well maintained if we keep only rank of 2 in this way. So it doesn't suffer from this issue where different nodes may have different sparsity pattern. So the more you communicate, they have different sparsity pattern. So actually it gets denser and denser. So this way, it doesn't suffer from this problem since it is sending the low rank version of the gradient tensor. Okay, so in summary, we talk about several gradient pruning methods, okay, including naive sparsification using local gradient accumulation. And the problem of that is actually the momentum, right? So we actually need to do the momentum correction to accumulate the velocity rather than accumulating the gradient. Okay? And then gradient tweaking and warm-up training can further help with the convergence. Okay, so we can achieve really high sparsity ratio, like 99.9%, without losing the accuracy. But the problem is that gradient will get denser during our reduce, which can be solved by power SGD using a low rank approximation to reduce the gradient size, which has actually been integrated into PyTorch. All right, so next one from pruning, we are going to switch gear to talk about quantization, right? Using fewer number of bits to represent the gradient. So this is a popular, very famous word called one-bit SGD. Yeah, question.
This is a basic question, but why is it necessary for the when you keep each other? I thought that we were looking at ways to reduce the fact.
Oh, that was covered in the last lecture. In case you missed the last lecture, we talk about the motivation for communication, right? Say we are using data parallelism, like worker 1 and worker 2, they each have several copies of the its own copy of the training data, right? They each get its own gradient, and they want to share the gradient to each other so that they can update the weight. Like you learn something, your classmate learned something, you want to exchange with each other to understand what each other learned. Right? So that's why we need to communicate the gradient. All right, so this is very similar to gradient pruning, right? So this is the original gradient vector matrix. Okay, so this is the one-bit version, and then we have a residual, okay, which can be accumulated and continue to be updated in the next time. So this is showing the diagram of one-bit SGD. Right? It's showing that we can actually use one bit for each gradient to be communicated. But that's not exactly one bit, since we have this column-wise scaling factor, right? So for each column, we are comparing whether a gradient is larger than 0 or smaller than 0. So this is larger than 0, this is smaller than 0. So 1, 1, this is -1, this is +1, right? So if we just put 1 and -1, that is actually not enough. So what do we do here? We have a column-wise scaling factor. Okay, so this is not 1, but actually 1 times the scaling factor called mu1. Right, and mu1 is shared for this entire column. Right? So it's actually a column-wise scaling factor. So this entire column is either +1 or -1. But scaled by the scaling factor called mu1. Right? So the second column is actually -1, -1, +1, -1, scaled by mu2, right? Which is the scaling factor for the second column, etc. Of course, using this quantized matrix, we will have quantization error. So the quantization error will be accumulated to the original gradient. Actually, apart from this method, actually people proposed threshold quantization approach. Right? So we can use a ternary representation. But previously, this is using a binary representation, either positive or negative. Right? So in this way, we can have both a positive, a negative, and 0. Right? So we have to empirically choose this threshold tau. Right? So everything larger than tau in green, everything smaller than -tau, this is in yellow, right? And something in between, it is in white. Right? So we'll have these 3 values, okay, tau, 0, and -tau. Right? Again, we can have this error matrix to be accumulated for the next iteration. Apart from that, there's also another work called ternary gradient matrix. So we can divide the gradient by the max of the gradient, okay? And we can quantize them to 0, +1, or -1. Okay? With probability using the magnitude of this gradient element divided by the max of the whole gradient tensor, such that after quantization, the expectation of the quantized value is equal to its original value. Okay. So if this G divided by max G is like 0.9, then you have 90% of probability to be quantized to 1. Okay. If it is so that actually the expectation will be well maintained. But this method doesn't accumulate the error, so the quantization happens on the fly.
What about adding like the noise? Because I've never done that.
Adding some noise.
Yeah, gathering and signal processing.
Usually adding noise helps with quantization. So I guess it might be helpful to add some noise. So far we talked about how to tolerate and reduce the bandwidth, right? So there's a second problem very critical, which is the latency. Right? So reducing the bandwidth is important, but reducing the latency is equally important, right? So the latency in a data center can be as low as like 1 microsecond, but in 4G, LTE, etc., it can be as long as 200 milliseconds. So how do we conquer this latency bottleneck? So bandwidth is easier to be conquered because we can always upgrade our hardware. For example, we can improve our networking card from like 10 gigabit per second to 25 to 100 or even 200 gigabit per second switch, right? Networking switch. And also we can use those gradient compression techniques to reduce the bandwidth requirement. However, latency is hard to improve because of the physics, right? So we are limited by the speed of light. So traveling from Shanghai to Boston, even at the speed of light, that require more than 100 milliseconds, right? So that is the physical limit we cannot improve. But if you want to do some distributed training, say some data is located in the US, sometimes some is located in other part of the world, how do we do distributed training across the world, right? So let's see the typical latency within the rack that ranges from a couple of microseconds to below 1 millisecond. In the same data center, that is between like 1 millisecond to 10 milliseconds. But wireless connection that is several hundred milliseconds versus across the world, that's hundreds of milliseconds. Right? So how do we enable training, distributed training to happen even keeping the higher training speed, but across different latencies, even much higher latency, something much higher than within a data center. So imagine we are using the vanilla distributed synchronous SGB. What happens for different workers, right? So we have to do computation, which is represented in blue, right? And then do the communication, and then synchronize. Do another computation, and do another round of communication. So what happens if the latency increases? So the yellow part of communication will become much longer. Right? The blue part is actually the useful work for computing the gradient. But a lot of time is actually wasted communication. Right? So as the latency increases, like the total training time will also increase. So how do we solve this problem? Okay. Can we allow this stale gradient? Okay. Previously, the reason we cannot start the second iteration of training is because we have to synchronize. Okay. We have to wait for the gradient of different workers to be communicated with each other. Right? So can we tolerate stale gradient? Okay? Just like we can use late days in our homework. Okay? Can we use late days in our homework just like we use that for communication, the gradients? The answer is actually yes. Okay? We can, allow stale gradients, okay, using the late days, okay, to allow those stale gradients to be updated so that we can overlap the communication with computation. We don't have to use the latest. We don't have to synchronize immediately, right? We can relax that, allow some staleness, so that we can overlap the communication versus computation. So let's see how that works. So this is different timestamp where iteration 1 we have to send it so that iteration 2 we receive that, okay? And iteration 3 before. So without delay, all the local machines are blocked, and they have to wait for the synchronization to finish. But if we allow some delay, right, we could allow some stale waiting. So when we are sending from iteration 1, say we can continue to the computation of iteration 2 and 3, right? So this is even without having received the gradient from iteration 1, right? So it takes a long time since it's a very long latency. So until iteration 4, and we finally received the gradient from everyone in iteration 1. Okay? So we can actually consume this gradient. That is actually happened 3 iterations ago. So that is actually the old gradient, the stale gradient. Right? So we apply that stale gradient, which should have been applied in iteration 2, but we actually apply them in iteration 4. Right? So there's 2 steps of delay. Similarly, for the gradient that was generated in iteration 2, it should have been applied in iteration 3 if the communication is fast enough. However, there's long latency, right? Communication is slow. The communication didn't finish in step 3, but actually finished in step 5. So we just take this old gradient and apply that in iteration 5. Okay? So this is actually the delayed gradient update, right? DGA. So we can tolerate this staleness and allow the computation to continue without being blocked by communication, right? So this is showing what happens when we are blocked. We have to wait a long time for the second step to actually begin. Right? So nowadays, now we can immediately begin iteration 2 without having to wait for the gradient to be fully communicated. So this is usually explaining what happens here. Right? So after iteration 1, communication happens. Right? So, but we don't have to wait, but immediately start the second iteration. So here we are actually already started the iteration even before the communication finishes. So as the network latency increase from this amount to a larger amount, right? It doesn't matter with respect to our total tuning time. So what is the limit that we can tolerate in this case? If the latency is longer than what, then we will be slower. So in this example, we are delaying the gradient by 1 timestamp. We can tolerate the most by 1 timestamp.
So the communication takes longer.
Right. Right, exactly. So the communication is longer and longer, and finally even longer than the communication, then we can no longer tolerate it. Right? So since we have to do synchronization up here. But before that, no matter how long that is, as long as fall into this range, we can just hide that latency. So this is shown in pseudocode what happens. So for each iteration, we calculate the local gradient, okay? And we send our gradient with the iteration ID to other nodes, right? And also we maintain this list, okay, indexed by the iteration, okay, with our own gradients. And then we receive the gradient from other nodes that happened actually d times ago. Okay? So something happened d times ago. So we are now at timestamp 4. And finally, we can receive the gradient that was generated in time 1, in t1. Right? So we receive that to get the average gradient from all the servers. Okay? So here we apply our own gradient, okay? And we receive the average gradient from d times ago. And we have to subtract our own gradient from d times ago, right? Which is in this list, maintaining a list of gradients of the local gradient, a local copy of the gradient. And so we are actually using the averaged gradient that was d times ago, use that to replace our local gradient d times ago. Okay? So we are consuming a stale gradient that is actually d iterations ago, but still that can converge. All right, so this is comparison about the conventional SGD versus delayed gradient aggregation. Previously, if you increase the communication, which is shown in yellow, the total training time will be longer. Right? But if using this new method, we can tolerate the latency since we are delaying the update, right, from here to here. So as long as the latency does not exceed this barrier, the total training time will not be impacted, so that we can overlap the communication and computation by using this stale gradient. So in this slide, actually, we are showing this example in a more concrete manner. Right? So here we have this 6 timestamps. At the 6th iteration, the average gradient from the 3rd iteration actually arrives. Okay? Similarly, for the 5th iteration, the gradient from the 2nd iteration arrives. For the 4th iteration, actually, we receive the gradient from the 1st iteration. Now, conventionally, we just apply the gradient update in this manner, right? This is a naive version, right? We receive something that is stale. Right? We use a late date of t. T is the number of timestamps that is representing the staleness. Right? So this is the average gradient that was generated d steps ago. Right? So directly applying such stale gradient will actually hurt the accuracy. So the more we delay, actually, without gradient correction, actually it loses up to like 4% of accuracy. So, which is showing that directly using the late day is not helpful. Does not work. Right? So rather than directly using this stale gradient, right, we have to actually subtract our own copy d times. So this is actually the gradient correction term. So after applying that, we can almost recover the accuracy, at least with a delay of 10 timestamps. Even with 15 timestamps, the accuracy is okay. But with 20 steps, it begins to drop. Okay. So this is the evaluation on image and also language data sets. Right? So we can show the speed up using delayed aggregation compared with other methods such as that average. The speed up is quite significant, like 3 times to 4 times, while maintaining the accuracy. So here we are actually having a delay of 20 steps, just like having 20 days of late day. Right? We can delay for like timestamp of 20 steps. Actually, we did the study using the setup with 8 Raspberry Pis. We stack 8 Raspberry Pis in a rack, and we have 2 such racks in the lab to actually have this to measure the speed up. So we measure from 1 node, 2 nodes, all the way to 8 nodes. Altogether 8 nodes in this Raspberry Pi 5 for both the region task and also for the language task. So with 8 nodes combining using this PGA, when we are delaying the update by 20 steps, 7.5 speed up compared with having only 1 node. And this is without those advanced like 25 gig Ethernet, right? So very long latency and low bandwidth. So with such technique, it made it possible for us to do like on-device training and bandwidth learning, which we are going to introduce in the future lecture. All right, so here's a summary for today's lecture. We talk about 2 bottlenecks for distributed training. Okay? One is the bandwidth bottleneck, and the other is the latency bottleneck. Okay? So for bandwidth bottleneck, we can shrink, we can compress the gradients using 2 methods. One is pruning, the other is quantization. So for pruning, the remaining gradient vector becomes sparse. Okay? So we have to do the momentum correction to actually accumulate the velocity rather than accumulate the gradient. Okay? And by using gradient flipping and also the warm-up training to further stabilize the training process. And also we can use even 1 bit or ternary gradient to save the communication bandwidth. With respect to tolerating the latency, okay, we can use this delayed gradient averaging to use late bits to allow staleness during the communication, so that we can actually pipeline or overlap the communication versus the computation, right? So that we can tolerate the latency in distributed training. If you're interested to continue to explore this area, we can give you this access to our Raspberry Pi farm for you to do some on-device training job. And we have only 2 such racks, so if you need access, talk to us early. All right, so these are some of the references we described in today's lecture. Okay, so that's all the content for this lecture.